en talare som kommer prata på engelska. Och det handlar om ämnet end-to-end. Någonting som vi också ibland hör kastas omkring som ett begrepp, ibland inom kryptografi och sen i chattar brukar man också prata om end-to-end encryption. Vi har med oss Nästan från KTH, Centrum för cyberförsvar och informationssäkerhet. Och det här kommer alltså ske på engelska. Och vi vill gärna också att frågorna kommer på engelska så att frågestunden går smidigt. Tack så mycket. Nästan, you may begin your presentation.
Yeah, thank you very much. So my name is Nästan. I'm a professor at the theoretical computer science division, actually it's called, at KTH, and in my research group we work with different ways of building highly secure systems security and provable security in particular. So I'm gonna try to be as little technical in this presentation as I can be, but I will try to explain in an understandable way what this means and what we can do with it. And in particular, I would claim that we can do a lot more than you probably think these days. Right. So let's get going and start with, there we are. Start with a simple scenario here. Well, not so simple perhaps if you're a cryptographer, but end-to-end communication on a wire or wireless between, say, a server and a mobile phone. For this type of application, cryptography is essential. And there's basically two ways of constructing and evaluating a crypto system today. So one approach is used for shared key crypto systems, where you have, shared keys between the various parties in the crypto systems, and another for public key crypto systems. And in the former case, state of the art in principle uses a lot of experience, a lot of testing, a bit of maths, a lot of simulation, and examples are many familiar ones: Twofish, Serpent, AES, and so on and so forth, as the slide says. Are they secure? Well, maybe, but we don't really know. There are no proofs that these things are really secure. It's a somewhat different story when we turn to public key crypto. In this case, we have maths and we have proofs. And examples are also familiar to many of you: RSA, LGML, Diffie-Hellman, and so on and so forth. Are they secure? Yeah, we have mathematical proofs in many cases, which, for that matter, requires theoretical and practical assumptions of various sorts. But at least we have something to work with. These assumptions are not trivial at all, and they are not guaranteed to hold, and there are issues with quantum crypto and so on and so forth that many of you will have heard about. But when we turn to the real world, things are quite a bit more complicated, because as a matter of fact, the information flow between the parties and the communication passes through a lot of other things than the ether or a wire. It passes through devices and modems, and processors, and so on and so forth. So the attacker has a lot more ways to intercept and interfere with the communication and the processing of the data and the processing of the crypto algorithms, for instance, than appears at the first slide I showed. Okay, so the question I want to raise today is it even possible to think about things like provable end-to-end security for systems that are as complex as this? I should say right away that provable end-to-end absolute security is not something that we can do. That's out of the question. There is no such thing as absolute security. But we can try to approximate and get as close to this as we can, and that's the theme of this story. And we do that in this in the talk today by presenting to you an experiment we did. Well, we are really at the finishing throes of implementing this experiment. And what we are doing is that we're building a system for electronic voting, and we're trying to get as close as possible as we can to provable end-to-end security, but with a reasonable effort. Okay, and the latter is absolutely essential, because as many of you will know, formal methods, which is what we're working with, are expensive and work-intensive things. So let me just show you the system, just to make things a little bit more concrete. The system we're working with, this electronic voting system. Many of the details in the picture here you can ignore. I'll just take you through it at very high level, just so you understand a little bit and you can get a feel for the complexity of this system. So at the start, we have a voting client. This is where the voter engages with the system. The voting client gets its software from a content delivery network. Once the voting client starts working, it interacts with an external authentication and registration service for the election. We use the FRIA ID service for this. And once this is complete and the vote has been cast, the voting client sends off a ballot to something called a vote collection server. This vote collection server, well, as the name says, it collects the votes until an administration client, a very rudimentary in this system, administration client, tells the vote collection server that the election is over, upon which the vote collection server will pass on in batch the set of encrypted votes to a cryptographic engine, a mixnet, which has the role of shuffling the votes in order to remove any traces of voter origin. Right? This is like, you can think of this like card shuffling. By card shuffling, and if the property of this mixnet is that if at least one of these mixers work correctly, then anonymity is guaranteed. So then, once this is done, we have clear text votes that are decorrelated with the actual voters that can be publicized somewhere on some webpage or something like that. So that's the system. Okay, so in this talk, we're particularly interested in the vote collection server. And just to make clear, what are some of the security concerns we might have? So the role of the vote collection server is, as I said, to marshal incoming ballots and to strip the ballot of the voter IDs that it receives from the voting client through the registration phase, checks that the registration is okay, collect voter IDs to prevent double voting, and passes on the votes to the mixnet. Now, should it be so that the vote collection server is compromised, then various things can happen. Election secrecy can be compromised. Votes can be dropped or falsified or duplicated or injected. Of these, some of these complications are really handled already by crypto, since the voter itself can check whether or not the vote that was submitted is actually in the final tally. But there is no such guarantees for vote injection. I mean the submission of fraudulent votes. And this is one of the key security properties that we're concerned about for the vote collection server. And a third complication is that the whole election process may be compromised. So I need to be a little bit clear about what I mean by end-to-end security and provable end-to-end security. For the purpose of this talk, the security properties we're interested in are basically the standard CIA wants confidentiality, that voter privacy is respected, integrity, that, for instance, you cannot inject fraudulent votes into the system, and availability, well, that everything will process step by step until the election is over. Then for e-voting, there's some additional specific properties like prevention of voter coercion and so on and so forth. We ignore those here. Now, by end-to-end, what does that mean intuitively? Well, it means that we want to secure the system from data input, basically physical data input to physical data output, including all processing steps. And a real-life system, as I indicated before, has a lot of processing steps. So this is not a trivial task at all. In this work, we're only addressing the software stack. We do not consider the hardware or the physical layer, or rather we assume that the hardware, the processors, and so on and so forth, act as according to their specifications with what is known as side channels and so on and so forth. And that, of course, is not true in the real world. So we have more work to do. Provable end-to-end security, in particular, means, in this work, the existence of a machine-checkable form of proof. Now, you can imagine, given the complexity and wealth of details that are involved in processing the entire chain of information and devices that a message needs to pass, that this is massively complex. These things get full of details and very large. So we have some real challenge on our hands here. The benefits of this is that we get explicit formal statements of proof of the security properties that we're interested in. We get as output, one way or the other, proofs or certificates that can be replayed and scrutinized in minute detail. And when applicable, which is in very many cases, we can construct proof fully automatically. Drawbacks, we need to be clear about the drawbacks of this approach. One drawback certainly is that proofs tend to get huge. Another drawback is that expertise in running these kinds of systems is not very commonplace. I mean, this is not a technology that's going to be used by the average developer anytime soon. That is clear. Still, we think it's of interest to examine this question. And to help us in this process, we have a number of tools, of which some have existed for quite a while, and some are new. Of the former type, well, we are working with cryptography, of course. I mean, that's absolutely essential for an application like this, and we rely on a state-of-the-art mixed library, verifierat, that was developed by Dr. Svigström, a colleague of mine at KTH. This is a very strong and well-implemented mixed-net library that's been used in national elections in Norway and Estonia, and it is currently being used in Spain and Switzerland and in the US. Those interested from US also in the system. So we just take that for granted in this work. This is not the primary object of interest for us. The second part of the toolbox, also something that's known since many years. I mean, it's in its sort of standard. We describe the desired behavior of this voting system in a theorem prover as basically a type of automaton that takes, it determines sequences of actions that we will allow and sequences of actions that we won't allow. And then in this particular case, this doesn't get too complicated, fortunately. It is sort of pretty clear in most cases what we want. The more recent and interesting pieces of kit, I would say, that we deploy are two. The first is certified compilation or verified compilation. And there's been real progress in the recent few years on this. There are two examples. One is CompCert from INRI in France. which is a theorem proof of grade verified compiler for C that won the 2021 ACN Software System Award. And the second one is KML from Chalmers, Magnus Muren's group in Chalmers, which is again a theorem proof of grade verified compiler, this time for a functional language. This won the most influential paper award in the most prestigious conference in the area this year. What these compilers allow us to do is to push security verification actually from not from source to binary, from binary to source. Right? So it gives us that the binary code acts in exactly the same way as predicated by the source, which is a very strong property and very useful property for our work, because we aim to secure things at the binary level. This completely eliminates compiler bugs and 0 days, and is really useful, as I hope I will show you. The second piece of kit that we use in an important way is a verified type 1 hypervisor that we developed at KGH in a project a few years ago. Basically, what such a hypervisor is a piece of software that runs at the most privileged level of the hardware stack, and it guarantees that we can partition the processor into several partitions, maybe at different security levels, in such a way that the two partitions do not interfere with each other in ways that we don't like. That's the intuition. And this is, as I will show, I think in the next slide, is something that is very, very useful and allows us to leverage and get much more bang for the buck in this kind of work. Let's see. Next slide. Here. I won't go into the proof actually of the security proof of this system in very great detail at all. I'll just show this slide and go over it very quickly. So basically, the proof is structured in, well, 3, maybe 4 layers, and at the top for the vote collection server, we have a single specification that I hinted at before that tells us, what sequences of actions are allowed and which ones are not. At the first step, we need to split this specification into 2 parts, 3 parts here, but it's really 2 parts. One, because we do not currently have a good embedding of the network interface into our framework. So we simply do not include this in the verification and leave this unverified, and I'll get back to that. And then we need a vote collection server core part, which is the one that implements all the functionality in the specification. So this we need to do manually, because this is very much application specific. Once we are here at this level, the work is basically over, because now we have a piece of high-level code that shows how the vote collection server core should act, which we compile to an executable form. Similarly, the assumed network interface is compiled in standard way and run inside Linux. Then, once we have the executables, we can execute everything on top of this hypervisor that I mentioned before, which will ensure that we can execute the VCS core on an actual processor with some additional paraphernalia in one partition and the network interface in another. And they won't interfere with each other than in the ways that we allow in order to realize the network interface functionality we're interested in. Now, some key points about this. This VCS core is developed as a standalone application. There is no operating system underneath the VCS core. All functionality that the VCS core, which is basically the network interface, it gets by controlled interaction with what remains of this Linux 5.15 network interface. This means for this particular setup that all vulnerabilities due to the operating system and the firmware are eliminated. Right. All applications that are critical to confidentiality or integrity, they run directly on silicon. The remaining software, which is unverified, can of course have security, will in general have security issues and bugs, but those cannot affect confidentiality or integrity. They can only affect availability. That's the price we pay, and that's one important reason for the almost in the title of the talk. So that's a sacrifice we pay until we can produce a formally verified network stack, which, by the way, we're working on at the moment. It also deserves to be pointed out that the virtualization, again, the use of this type 1 hypervisor provides a strictly controlled execution environment. And fourthly, since we're using such a minimal administration interface, this protects against tampering a lot. There is no way for an adversary that gains access to this interface to launch new threads or anything like that. That is just not possible. So what have we achieved in this work? Well, we basically have a proof of concept. We can build a fairly complex distributed system and the components that go into it with almost end-to-end guaranteed security properties at the binary level. So this, I think, is new. The system works in simulation, and we are working on this to get it working for real at small scale on this actual processor. The cost of the work, basically what we did was, the work we did was by a postdoc that has, with strong theorem proving skills, worked for 1 to 2 years to build up this framework. Of course, if we do it again the second time, this will be much faster. And it has to be said, of course, that we're importing a lot of components. In particular, the mixnet work, which is, result of at least or I think probably several decades of work actually. But that's another story. What are the limitations of this result? I think one thing to talk about is scalability. In order to scale this, one of the ingredients that we need is more advanced formal processor models. The models we use at the moment don't have too many features. So if one wants to do something more complex, one will have to reflect the features of more advanced processors. There are limitations to what we can do in terms of hardware features. It is well known by now that the the CPUs themselves are full of side channels in all sorts of ways, and protecting it against these is subject of ongoing research. We work on this ourselves quite a lot, and this is really a key problem in order to scale this up and to close some of the channels that we otherwise abstract from by saying that we just work at the software level. Then there's other scalability issues that, of course, that concerns just the task of producing more complex types of applications, because at the end of the day, the functionality of this core component, the remote connection server, is quite simple and straightforward. For real applications, this is going to be hard, of course. But just for a word in conclusion, I put this little statement on the slide here. Well, maybe, I mean, in my opinion, the work should be of interest. We're really dramatically increasing the security of this particular system. And if it's the case that work along these lines catch on, then there is a prospect in 5 to 10 years' time to build systems that are really dramatically more secure than the ones we have to grapple with today. And that will certainly benefit all of us one way or another. Thank you for listening. And if there's any questions, I'll be happy to discuss.
This is quite hard to implement in a real world scenario today. And you mentioned like 5 to 10 years. Is that what you think is the most realistic scenario?
When I'm talking about scalability and implementing this, we have a system. The system we're looking at, I presented today, can perform a small election from end to end. So it can be used in order to produce an e-voting system that can be used at scale. We can, in principle, implement this using the technology we have now. We need to get slightly more advanced models, but we could produce it. So when I'm talking about scale, and 5 to 10 years, what this means is that we are not going to get an army of theorem provers out in the wild, as developers in like next month or next year. That's going to take a while, and that's going to require some success stories that makes this interesting. I think this, at the end of the day, is the real bottleneck for wide-scale use of this technology. So yeah,
I understand.
Yeah.
Do we have any questions from the audience? We have 2. What kind of language would be of interest to implement a system like this? Are there any consideration for memory-safe languages, such as Rust, or is C the way?
Yeah, that's a very good question. Yeah, Rust is obviously interesting because it is claimed we are working with theorem provers, so we want mathematical theorems. Unfortunately, Rust doesn't have a formal semantics, and that prevents us basically from proving theorems about it. Of course, it's possible, very possible, that Rust will receive such a semantics in the future. Then we can do it. It's even possible that we could do it here, but it's not on our agenda right now. So absolutely, there is room for languages like Rust. It will help developers produce code with fewer bugs, but ultimately we're working at the binary level, using as much automated techniques as possible. So we are quite happy working with binary code, raw binary code, except that it's obviously complicated and requires tools. I think actually tools is a key thing, is a key artifact for this kind of thing to scale up, right? I mean, as I hope you got out, the message you got out of my presentation was that actually we don't have to do that much given the tools we have available already. We are reusing a lot of stuff. We are reusing a crypto engine. We are reusing certifying compilers. We are reusing hypervisors and stuff. That allows us to really do this kind of work. And that's the future, definitely.
And there's absolutely room for changing these tools, and the tool set is that can be changed in the future as well.
Yeah, sure, of course. This is continually developing.
Do you have any more questions? Do you see realistic use cases for this method? Most software today runs on top of very complex environments and also depends on a lot of libraries and other dependencies.
Absolutely, sure. That's also a very good question and a challenging one. Let's be fair. Ultimately, the way to success, if there is one for this kind of thing, is structure, divide and conquer, build up gradually usable libraries that are certified, and without once we have more of those, we can do more interesting, more productive things. And by using techniques like virtualization, for instance, we can compartmentalize systems more, with well-known interfaces, well-understood interfaces, control, which is key. Always is key to security for these kinds of things. So, yeah, I mean, it's challenging, absolutely. I do think there are ways forward in spite of the complexity. In fact, structure and well understood interfaces are key to master this complexity. There's no other way.
Any more questions? Would you say that further research, particularly concerning the limitations of scalability, is best performed in an international environment, or should geopolitical issues be taken into account when developing this further?
Thank you for the question. That's a very topical one, I have to say. I was involved in discussions on this topic just on Monday. Earlier I would say, like 2 years ago, I would say it's absolutely best performed in an international environment. We are taking, research results, open research results, and using those all over the place. So absolutely, that's essential to get speed, get critical mass, all sorts of things. But we can't deny the geopolitical issues. But I'm not sure I'm the one to. I can say that I'm aware of it. I'm aware of the complication, but we shall see.
Yeah, sadly, the geopolitical issues have crawled into every research that we have.
Yeah, that seems like it.
Do we have any last questions? In this context, what is the value of secure computing enclaves as a platform for execution?
It is of very high value. Short answer, of very high value. When we're talking about a type 1 hypervisor and partitioned execution, as I did, that's basically what we're doing. We are building a secure computing enclave. We are not encrypting memory, things like that, but it's basically the same thing.
And last question? No? Oh, one more. What are the experiences of the people used as test subjects?
We don't have any test subjects. This is too early, and frankly, I don't think we will be using test subjects either, because I don't think the processor that we are working with is just too feeble to do any elections at interesting scale, and that's not the purpose of it. The purpose is of proof of concept. So yeah, but it's an interesting question. Yeah, thank you.
Okay, I think that was the last question. Thank you very much, Nästan, for presenting for us today. Thank you very much.
Thank you very much, Matthias.